So let's look at the concept of the dot product. Geometrically, if we had two vectors that started at the origin, so let's draw it in 3D, and then we can generalize it to 2D as well. So let's draw it in 3D first. So if we have two vectors that start at the origin, and there's an angle between them, let's call it angle theta. Let's call this vector A down here, vector B down here. So if these things are true, then we could just say the dot product of A and B is equal to the magnitude of vector A times the magnitude of vector B times cosine theta. And we can use this to find angles between vectors, but operationally, when in terms of actually taking the dot product, if we had two vectors, vector A goes from A1 to A2, dotted with the vector B, which is B1, B2, it's going to be equal to A1 times B1 plus A2 times B2. And this is the dot product represented in R2. But if we did it in R3 in 3 dimensions with vectors A and B, it would just be the same pattern, just 3 times. So A1, B1 plus A2, B2 plus A3, B3. That would be in R3. So let's do a few example problems of finding the dot product between two vectors. So let's do vector A, which is equal to 1, 2, dotted with vector B, which will be equal to 3, 4. Using our little expression A1, B1 plus A2, B2, we can just see that our dot product is going to be equal to 1 times 3 plus 2 times 4. And simplifying this, we'll have 3 plus 8, which is equal to 11. And one thing to note about our dot product is that it will always give us a scalar. So when we find the dot product, it's not going to leave us any sort of function value. It's always going to give us a scalar or just a constant. So it's fine that it equals to just 11. So let's work on another example problem, but let's do this one in R3 and make it a little bit more complicated. So let's have our two vectors. We'll have vector A is equal to 5i plus 2j plus k. And vector B can be represented by I minus 5k. So let's find this dot product. As we can see, it's represented with the letter notation with the vector hats instead of with our brackets like these. So let's change that first in our problem so we can see what we're working with. So vector A will just be 5, 2, 1. Dotted with vector B, we'll have 1. There isn't any j, so we'll have 0. And then minus 5 for our k. So if we perform our dot product operation, we'll have 5 times 1 plus 2 times 0 plus 1 times negative 5. And we'll see this is equal to 5 plus 0 minus 5, and that will just all simplify to 0. So when our dot product is equal to 0, that tells us something special about our two vectors. So when our dot product is equal to 0, it means our vectors are orthogonal to each other. And orthogonal is just a fancy way to say perpendicular. So that means our two vectors, vector A and B, have to create a 90-degree angle, or in radians, pi over 2. They have to create a 90-degree angle if their dot product is equal to 0, and that's a special property for dot products. So we can actually prove that when our dot product is 0, that our two vectors, vectors A and B, that they are orthogonal to each other, so that they're perpendicular. So how can we prove that? So earlier we said that 90 degrees is equal to pi over 2 radians. And let's just draw our cosine function. So our cosine function starts at 1, and it goes down to 0, goes to -1, back up, and ends back at +1. And then let's draw our 4 intervals of pi. So we'll have 0, pi over 2, pi, 3 pi over 2 over here, and then our last one right here is 2 pi. So we can see for our cosine function at pi over 2, it is a function value of 0. So let's write the theorem for the dot product. So A dotted with B is equal to the magnitude of A times the magnitude of B times the cosine theta. So if we plug in cosine of theta, if we plug in theta is equal to pi over 2, we just proved that we'll get a function value of 0. So we'll have A dotted with B times their magnitudes times 0. And then since their magnitudes are scalars, or they're just any constant times 0 is going to be equal to 0. So when their dot product is equal to 0, it means the two vectors have an angle between them of 90 degrees. So an application to the dot product would be our projections. So let's say we had two vectors. We'll call this vector B, and we'll have one down below called vector A. Given these two vectors, let's say if we moved vector B onto A, how far along on A would that go? So that how far away is going to be an answer to our scalar projection. And remember, scalar is just a constant. So how far along, we don't want to know how far and how long. We don't need to know both parts of our vector. We just want to know how far along. So we'll have our scalar projection of B onto A, which we write down as comp B sub A. And that is equal to the dot product of A and B over the magnitude of A. And now let's say if we did actually move vector B, what would that vector be? So now we have an actual magnitude and length instead of just the length. So we want to know the actual vector. So our vector projection of B onto A can be written down as the vector projection of B onto A can be written down as the projection of B onto A, which is equal to the scalar projection. So we'll write that first, comp BA times the unit vector of A. And if we just write that down to see everything, we'll have the dot product of A and B over the magnitude of A times vector A over the magnitude of A. So given two vectors, vector A and B, find their scalar and their vector projections. So let's find comp and proj. There we go. So let's find the two. So first I would recommend finding our scalar projection. So our comp of B onto A is going to be equal to the dot product of A and B all over the magnitude of A. So let's find our numerator first. The dot product of A and B, we write that out as 6 times 5 plus 7 times -1 plus -6 times 1. That'll simplify to 30 minus 7 minus 6, and that is equal to 17. So that's our numerator. To find our denominator, we have to find the magnitude of vector A, and to find that, we'll just use the distance formula. So we'll have 6 squared plus 7 squared plus -6 squared. That's going to be 36 plus 49 plus 36. It'll be 72 plus 49. And that is the square root of 121, which simplifies to just 11. So now if we put that all together, our numerator of 17, and then our denominator of 11, that's going to be equal to our scalar projection. So let's make some room. So we'll have 17 over 11. Now let's find our vector projection of B onto A. And before I wrote it out as the scalar projection of B onto A times the unit vector of A. So the only extra step that we have to do to find the vector projection is to just find the unit vector of A. So we'll have the vector A, so 6, 7, -6, all over the magnitude of A. And before, we've already found that, which is 11. So we'll have 6, 7, -6, all over 11. Now that we found our unit vector right here, we can just multiply it by 17/11. So we'll have 17 over 11 times that unit vector. And when we multiply everything out, we will be left off with 102 over 121, 119 over 121, and then -102 over 121. And then that is our scalar projection. So for some tips for the dot product, I would recommend, first off, to always write it out. So until you familiarize yourself that the dot product is a vector operation instead of multiplication, you should always write it out. So instead of doing this in your head of saying, well, 1 times 3 is 3, plus 2 times 4 is 8, so 11. Sure, pretty simple enough to do it in your head, but in order to correct your work easier when you eventually mess up, you should write it out. So we'll have 1 times 3 plus 2 times 4. And this just gets you into the habit of separating it from the idea of multiplication. And that leads off to my second tip, which is if you still write out your multiplication like this, you should stop. Because you're going to be doing stuff with dot products now in Calc 3. It's going to be confusing. If you look at this, and you still see multiplication. So just those 2 tips of always writing it out, and don't write your multiplication as a dot anymore.